Laura, can you hear me?
Can you hear me? Hello?
You can hear me?
Yes, yes. Can you hear me?
Okay, great. I can hear you. Yeah. Okay. You can start.
Okay, and I forget, how do I make it go to full screen? Is it that one? Okay. Is that working? Okay. Oh, okay. Sorry, it's scrolling by itself. Okay. I don't know how to get it. Just keep scrolling. Not. Okay. So hi, I'm Laura Engelbrecht. I'm a postdoc at ETH, and I'd like to thank the organizers for the opportunity to speak today. I'm going to talk about shift symmetries and the AdS CFT correspondence. This is work I did in collaboration with Aaron Blauvelt and Kurt Hinterbichler, which can be found in this archive paper here. Okay, so this is an outline of what I'm going to cover today. So I'm going to start by reviewing shift symmetric theories in flat spacetimes. Then I will introduce them in AdS and show you how some of their properties change. Then I will discuss the properties of the CFT duals of these shift symmetric theories in AdS. Finally, I will show you the results that we found for our AdS CFT computations, and then give a quick summary and discussion. Okay, so shift symmetric fields in flat space have been of interest for a variety of reasons. They provide useful classifications of low energy EFTs. They appear in spontaneous symmetry breaking. They can lead to non-renormalization theorems. They have enhanced soft limits and scattering amplitudes, which means that if you're looking at a scattering amplitude and then you take the limit as the momentum of one of the external legs vanishes, then the amplitude will vanish with the power of that momentum, and when there's shift symmetries involved, this power will often be higher than naively expected. And in exceptional cases, we can use this property to actually bootstrap the scattering amplitudes for these shift symmetric theories. The simplest example of a shift symmetric theory is a free scalar in flat spacetime, which is shown by Lagrangian here. And this is invariant under an infinite tower of shift symmetries, where shift symmetry is something of the form where you take the field and you take it to phi, you take phi to phi plus a constant, and that's the shift, plus you can have these other pieces as well, where you can have something that is linear in the spacetime coordinates, quadratic, cubic, etc. So where these x's are just your spacetime coordinates, and it looks like there's some, okay, there's weird like things happening on my screen. Okay, hopefully it's not happening on your end. Yeah, and these C's are just rank K symmetric traceless constant tensors. And so we call a symmetry of the form C times x, k x's a K level shift symmetry. So K just counts the number of x's that you have. In flat space-time, shift symmetric theories are always massless, and this is because this is due to Goldstone's theorem. Here, in addition to a free scalar, we can also have interacting examples in flat spacetime. So here are some examples. At k equals 0, which is just a shift by a constant, you have the P of x theories, which are any theory with at least one derivative per field, where x is d mu phi, d mu phi. At k equals 1, which is where you have, in addition to the just the constant piece, you also have a piece linear in x. And theories that are invariant under this type of shift symmetry are things like dBi, which naively you might think would only have a level 0 shift because it looks like the form of a P of x theory, but actually it's invariant under this higher order shift symmetry. Another example is Galileons, which have actions of the form where you take the field and then you have these symmetric polynomials that come in some certain combination, which are just functions of two derivatives acting on the field. These are theories that are often used in cosmological models and are well known in cosmology. So those are another example of k equals 1 level shift symmetric theories. At k equals 2, you have the special Galileon, which is just a particular combination of these Galileons, and it's additionally invariant under this higher order shift symmetry, which is quadratic in the x's and then also has this field dependent piece. And so that is just where you take the quadratic Galileon and then add the quartic Galileon to it. And then for k greater than or equal to 3, there are no known ghost-free interacting theories with higher level shift symmetries like this. Okay, so now let's go to AdS. So shift symmetric theories in AdS, unlike in flat space-time where they were massless, actually have masses. And these masses depend on the shift level k, the space-time dimension d, the AdS radius L, and the spin S. So for the scalars, you can see it looks like this. And then for, gosh, I don't know what, it's like a rate, it's doing weird stuff when I move the cursor. Anyways, okay, so, and then for the spinning fields, it looks like that there. Okay, so, and these theories, the free theories will just, their equations of motion will be the Klein-Gordon equations, which for this scalar field takes the usual form, and then this is what it looks like for the spinning field. And then you also have the constraints of transversality and tracelessness and all the indices. Okay, so the shift symmetry in AdS takes this form where S is a constant traceless tensor with the symmetries of a 2-row Young tableau. And these x's are the embedding coordinates of the AdS spacetime in a d+1 dimensional auxiliary flat space. So this is just like if you were to, take a circle, which is a 1-dimensional surface, and then embed it into a 2D flat spacetime. That's the same thing that's going on with these x coordinates. And then the little x's are the actual coordinates on the AdS surface. We also know of some interacting examples in AdS. So here are some scalar examples. At k equals 0, we again have the P of x theory. At k equals 1, we again have Galileons, but they're the AdS version of the Galileons. And if you take the limit that the AdS radius goes to infinity, then they just reduce to the flat space Galileons. At k equals 2, we have the AdS special Galileon, which takes this really complicated looking form. Unlike in flat space-time where it was a linear combination of regular Galileons, it's a completely separate object. In the flat space limit, it does reduce to a linear combination of the flat space Galileons, but in anti-de Sitter space-time, it's completely separate. For k greater than or equal to 3, again, there are no known ghost-free interacting theories. Okay, in addition to scalars, we also know of some vector examples. So here are 2 k equals 0 vector examples. There's one that just has this cubic and quartic interaction, and it's invariant under just shifting by a constant vector. Then there's also this more complicated looking one that has actually an infinite number of interactions. Here I've just written what it looks like up to quartic interactions. And it has a rather complicated looking shift symmetry, but it's still just a level 0 shift symmetry. And if you try to truncate this theory at any order, then it will ruin the shift symmetry. So the shift symmetry really requires this infinite number of interactions. You can construct shift symmetric theories as a decoupled longitudinal mode of massive fields as they approach their partially massless values. So partially massless values occur for spinning fields at the mass values shown here, where T is the field depth. And a massless field is a type of partially massless field which occurs at the depth T equals S+1, or S-1. Here's an example of what I'm talking about. So we could consider a massive vector as our parent field, and then if we take the massless limit, then our parent field will be a massless vector, and then you'll get a shift symmetric longitudinal mode. That in this scalar field, unlike this is just a massless scalar, and unlike in flat spacetime where it was invariant under an infinite tower of shift symmetries, in AdS it's only invariant under the k equals 0 shift symmetry. Another example is this massive graviton. You can take the massless limit of it. So for a massless graviton, this L m equals 0 is just the linearized Einstein-Hilbert action, which I didn't feel like writing out, and then you add this mass term shown here. And if you take the limit that the mass approaches 0, then you'll get the massless graviton plus this massive vector theory with a particular mass that makes it shift invariant. And this is invariant under a k equals 0 shift. Another example is this massive graviton where you take the partially massless limit. So if you set the mass squared to -2/L squared, then you'll get the parent field to be a partially massless graviton, plus you'll get the shift symmetric k equals 1 scalar field, where this is just your Galileon. Okay, so now that I have gone over shift symmetric theories in AdS, this comes to our main question, which was, does the shift symmetry in AdS manifest itself in the dual CFT operators, and if so, how? So a given field on AdS of mass m and spin s has a dual CFT operator on the boundary in one fewer dimensions with a scaling dimension related to the AdS mass by this expression here. So you can see how it is for scalars and then how it is for the higher spin theories. And then of course you can invert this to solve for the conformal dimension. And what you find is that there are two different possible conformal dimensions for this dual CFT, which are delta plus and delta minus. And for our shift symmetric fields, the scaling dimensions that are dictated by the masses are delta plus equals d plus s plus k, where d is the space-time dimension of the CFT, and s is the spin, and k is the shift level, and then delta minus is minus s minus k. So here's an image that maybe will help you visualize where these shift symmetric theories occur. So the CFT duals to the shift symmetric theories that have the delta plus scaling dimension are shown with the black dots. The delta minus ones are shown with the red dots. And then on the other side, we have the, my thing is scrolling. Sorry, it just started scrolling without me doing anything. Okay, so the partially massless parent fields are shown in the blue with the delta plus root, and then the delta minus root for the partially massless parent fields are shown in purple. And how this works is that you can, so if we want to, oh yeah, and I forgot to say that, yeah, the y-axis is the scaling dimension and the x-axis is the spin. So here you would have spin 0, spin 1, spin 2, etc. So if we were to take, for example, that parent massless vector, that would live here, and then it's to find its shift symmetric offspring, you would just reflect across this line here, which would lead to a this massless scalar, which would live here, and that's a k equals 0 shift. And so these diagonal lines tell you the shift level. So similarly, we also discussed the spin 2 field. So the massless spin 2 field that is the parent would live here, and its shift symmetric offspring would be the massless vector living here. And then the partially massless graviton would live here, and its shift symmetric offspring would be the scalar here with this k equals 1 level shift. So that's how that works. So let me just review some of the properties of CFTs. So there is a unitarity bound for conformal primary operators. So for a theory to be unitary, the conformal dimension needs to be greater than or equal to d over 2 minus 1 for scalars, and s plus d minus 2 for spinning fields. And for shift symmetric theories, the positive root of the scaling dimension lies above the unitarity bound, whereas the negative root lies below the unitarity bound for our shift symmetric theories. So we're ultimately going to be interested in this work just in studying the free theories for these shift symmetric theories. And we aren't going to be considering interactions, so we're actually only going to be computing the 2-point functions. And in conformal field theories, the 2-point functions are completely fixed. For scalars, they would just go like 1 over the distance between the two operators raised to the power 2 times the scaling dimension. And then for the spinning theories, you also have these this I structure, and you just take the symmetric traceless part of these I structures to get the 2-point function for the conformal field theories. So you might think, well, this must just be the end of the story. What more is there to say? Everything's completely fixed. But this is actually not the end of the story, and I will show you that there is more to say for these shift symmetric theories. You can start to see how the shift symmetry acts by considering the near boundary Pfefferman-Graham expansion. So if you consider this expansion for a given spin S field of generic mass, then it will have 2 leading fall-off behaviors, which in Poincare coordinates takes this form shown here. So there'll be a piece that goes like z to the delta minus s, and then a piece that goes like z to the delta plus minus s. And the first piece we call phi 0, and the second piece we call psi 0. And so this is supposed to be for a spinning field, and actually we only need to, for this discussion, we only need to consider the component of the field that doesn't have any z-directed pieces, and that's because they are related to this piece by the equations of motion and the constraints. So in standard quantization, phi 0 is proportional to the source and the CFT is generating functional, while in alternate quantization, it's psi 0 that is proportional to the source. Okay, so now let's focus on our shift symmetric scalars. For our shift symmetric scalars, the delta plus conformal dimension is d plus k, and the delta minus 1 is minus k, and the near boundary expansion takes this form, where the phi 0 piece falls off like 1 over z to the k, and the psi 0 piece falls off like z to the d plus k. Okay, and if we now apply a shift symmetry to our Pfefferman-Graham expansion, then what we find is that the phi 0 piece is unaffected by, is affected by the transformation. So it transforms in this way, where these x tildes are the embedding coordinates just evaluated on or projected to the AdS surface. And psi 0 is unaffected by a shift symmetry. So what this tells us, in standard quantization, we have to fix psi 0 at the boundary. And since it's the one that gets affected by the shift symmetry, this means that these boundary conditions break the shift symmetry. However, in alternate quantization, we have to fix psi 0 at the boundary. And because psi 0 is unaffected by the shift symmetry, that means that these boundary conditions are compatible with the shift symmetry. Yeah, you can do the same thing for the spinning fields. And so for the spinning fields, you get delta plus value to be d plus k plus s, and for delta minus, it's minus k minus s. So this is what the Pfefferman-Graham expansion looks like. And if we look at how the shift symmetry affects this, again, we find the exact same results. So we find that phi 0 is affected, but psi 0 is unaffected. So standard quantization breaks the shift symmetry, but alternate quantization is compatible with the shift symmetry. Okay, so now for our AdS CFT computations. So for this, we use the holographic renormalization procedure, which is outlined in this paper here by Bianchi, Friedman, and Skandaris. So this procedure just follows these steps where you use the equations of motion to find the asymptotic solution in terms of the two pieces of boundary data, phi 0 and psi 0. You then regularize the action by cutting it off near the boundary. You then construct the counterterm action from all the possible local functions of the field. And then you renormalize the action by adding the counterterm action to the regularized action and then tuning the coefficients to cancel off any divergences. And this will give you then a finite renormalized action. So when we do this, we find that the renormalized action is, for our shift symmetric theories, looks like this, where for standard quantization, again, we identify phi 0 with the source, and then for alternate quantization, we identify psi 0 with the source. Okay, so now for our results. So for our shift symmetric scalars, we found the renormalized action to take this form, which leads to a position space correlation function for the CFT dual to take this form shown here, which is the canonical structure of the two-point correlation function of a primary field. So this is what you would expect. You have 1 over x to the 2 times the conformal or the scaling dimension. Okay, and then here are results for alternate quantization. So for alternate quantization, we found this renormalized action, which leads to the position space correlation function that looks like this. So it takes this logarithmic structure. So it has this x to the 2k, which is the right, what you would expect for a, which is the right form for a conformal primary, but then it has this logarithmic structure, which is not the correct form. So this violates the canonical structure. So what's going on? Well, this is very analogous to the case of a free massless scalar in 2 dimensions. So for this familiar case, where you just look at a free massless scalar in 2 dimensions, the two-point function, which is often given in complex coordinates, z and w, where here z is not the same z I've been talking about in the previous slides, but it's just what I denote the coordinates by, then you also get a logarithmic structure, which is shown here. And how we interpret this is that phi is not a primary operator. However, acting with the derivative with respect to z on phi is a primary operator of spin 1 in conformal dimension 1. So the two-point function of this, if you compute the two-point function of these primary operators, then you do find the usual structure, which here is 1 over z minus w squared. Okay, so back to our shift symmetric theories, we can apply this same kind of idea. So we found our logarithmic structure, which implies that our operator was not a primary operator, but we can construct one by taking k plus 1 symmetric traceless derivatives acting on the operator. And when we do this, this leads to correlation functions that correspond to a primary field of spin k plus 1 in conformal dimension 1. So these ones have the proper expected form for primary operators. So back to our picture, what is going on is we were looking at the red fields here. These are the ones found by alternate quantization. And then when you apply the derivative, that takes you across this line here and reflects it over back to the parent fields with the delta minus conformal dimension. So we were looking at scalars, which happens on this s equals 0 line. These are the different shift symmetric scalars. And then when you apply the derivatives, that takes you to these scalars here, which are these weight 1 scalars. Okay, so I've been a little bit cavalier in my explanation. So when we considered the Pfefferman-Graham expansion, there's actually really 2 cases that we need to consider. So what I talked about before was actually just the results for what we find in odd dimensions. However, in even dimensions, the Pfefferman-Graham expansion, you also have to include these log of z pieces because those are also solutions to the equation of motion. So for even dimensions, let me tell you what we find. So for standard quantization, we find the exact same thing that we had before. We find the canonical structure for our 2-point functions, 1 over x to the 2 times the conformal dimension. However, in alternate quantization, we find a renormalized action that looks like this, where it has a 1 over log of momentum. Unfortunately, this is not conformally invariant, and neither are any of its derivatives, so we don't yet know how to interpret this case. We also looked at vector cases. So we looked at holographic renormalization for shift symmetric vectors. The procedure is the same, but just has more complicated expressions, and we found very similar results where for standard quantization in both odd and even dimensions, we find the usual structure. But in alternate quantization in odd dimensions, we again have this logarithmic structure. So it doesn't take the form of a primary operator, but we can create one by acting with derivatives on the primary operator, which will create a spin k+2 operator with scaling dimension 0. And then we get the usual expected form for a 2-point function. And again, we have this issue in even dimensions where we get 1 over the log of the momentum, and we don't know how to interpret that. We expect the same pattern to occur for the higher spin theories. And so that is our main result. So just to summarize, the CFT dual attained by standard quantization breaks the shift symmetry, and this leads to 2-point correlation functions in position space with the canonical form for primary operators. However, in alternate quantization, which preserves the shift symmetry in odd dimensions, we find correlation functions with logarithmic behavior, which violates the canonical form for the primary operators. The shift invariant field strength, however, can be constructed by taking k+1 traceless symmetrized derivatives of the operator, which will give a primary operator of spin s plus k+1 in conformal dimension 1 minus s. And so what this is telling us is that the physical operators are only the ones that are invariant under the shift symmetry for alternate quantization. Just a couple of points to discuss. There are some AdS flux vacua that have been found to have the dual operators with integer conformal dimensions. So those are given in these papers here, and I'm guessing that means there's probably a shift symmetry lurking around. Also, some interesting things that we might look at in the future would be to consider interacting shift symmetric theories, which we expect to exhibit interesting behavior because in flat spacetime, they exhibit interesting behavior. And then also, we would like to understand what is happening with alternate quantization of the shift symmetric theories in even dimensions.
Okay,
So
Laura, thank you very much for the nice presentation. Are there questions? We can take some questions. No questions? Okay, then our next speaker is Carlos Nunes from University of...
Yes,
there is a
question.
I can't hear.
Can you hear me?
Is there a question?
Can you hear me?
Yeah, is there
I
a
do
question?
have a question. So, hi, first, thanks for the talk. The question is, usually in AdS CFT, in the dictionary, we know that gauge symmetries in the bulk are dual to global symmetries in the boundary theory. Here, you're talking about global symmetries in the bulk. And I guess my question is whether your results shed new light on the kind of symmetry structure that this implies for the boundary theory, since usually we don't really want to have global symmetries in the bulk.
Yeah, I don't know. This is something I haven't thought about a lot. And I guess even if you don't want to have full global symmetries, you might have approximate symmetries.
So I didn't read your
also
paper
be
in
interesting
detail.
for approximate symmetry.
There's a statement in the abstract that the shift symmetry
yeah, I
is
don't know. I'd
realized
have to
as a
think
gauge
about it
symmetry
more.
of the dual CFT. Could you maybe comment on that? So maybe
yeah,
that's just me, but I didn't quite get from the talk.
I'm not sure what
in what
more you
sense
want
I
me
should
to
think
say.
of
Like,
it
yeah, it
as a
behaves like
gauge
a
symmetry.
gauge symmetry.
That's okay. Thanks.
Sorry, I'm not sure how to answer that.
Okay, let us thank our speaker again. And if there are no more questions, we can actually start the next talk. Carlos Nunes will be speaking about aspects of gauge string duality. He's from